Good evening. Do you want to start the meeting?
Yes. Yes, please.
Yes.
Yes.
So basically, we are here to practice lecture 3. So I will open the slides of the questions that we should solve together. Wait a moment. I will share the screen. And basically, the idea is to solve the exercises together. Last time I gave students the possibility to work, to use breakout rooms, but after we did some polling, I understood that students didn't like the idea. So I will ask, we will start also to use breakout rooms, and you will give me the answer if you want to continue with breakout rooms or not. Okay, so basically we want to solve the exercises that I mentioned during the lecture. So we will start from the first exercise. And the first exercise was, okay, wait, you shouldn't see the solution. Wait, I will try to fix the slides, animation, flying in, but basically, okay. Now when I use share screen, it should be okay. What is breakout rooms? I can divide you into smaller groups that you will work together. I don't know if some of your lectures used it, but for the practice exercise, it's a good idea that when I ask the question, you try to solve it together in a smaller group. I can join each group, and you can later share the results. But in the Hebrew group on Monday, some of the groups were very active, and that is the whole idea, to study, to not to be passive learners, but to be active learners. But some of the groups didn't have any activities, and they were divided in a group of something like 4 students. But here, maybe we are a smaller group. Currently, there is only 12 students, and one of the students is my tablet. So you are only 11 students. So basically, the breakout rooms may be not so important to create. Okay, I will remind you the idea of regular languages. To prove that some language is a regular language, you have to build deterministic finite state automaton, or maybe you can use non-deterministic finite state automaton. But currently still, we are still using deterministic finite state automaton. So basically, I'm giving a word W, A1, A2, A3 that has letters in it over some sigma. And now we have to prove that the language LW, which has only one word W, is a regular language. So basically, I would like you to take, let's say, 2 moments and try to figure out how will you construct the automaton that proves that this language is a regular language. Please pay attention that you are not giving not the alphabet, not the concrete N. N is, from our point of view, is some kind of variable. We are not giving a specific value. So any ideas? Someone wants to share?
Instead, would it be better to define the formula for building the automaton? Because it's by N, so you'd be instead of like drawing out how it looks, you have to draw out how it would look for each N, like how formula of how to build it, right?
Yes.
Okay.
So basically, not construction. You just have to build it by construction. So let's start to analyze. I will start building the automaton from the state Q0. And on first letter, where should I move?
W.
Okay, so let's see the automaton. I don't know the length of the word. I know that it has n letters, but n is a variable. So I'm building the word W here. All the letters of W are actually written here. So I'm moving with the first letter to the state Q1, with the second letter to the state Q2. With the nth letter, I'm moving from the state Qn minus 1 to the state Qn. And for the rest of the letters, please pay attention. I used S instead of sigma because I'm using the application that doesn't have a letter sigma. So when I want to say that I want to move to the state Q4, which is a trap state, I can't go from the state somewhere, trap. So I'm basically at the trap state. So I'm moving to the trap state each time when I see any input that differs from the current letter that I supposed to accept. So if I supposed to accept A1, then for the rest of the letters, which is sigma minus A1, I am moving to Q4. If from Q1 to Q2, I suppose to meet in the word W, the letter A2, currently I am moving from Q1 to Q4 to the trap state each time that I see all the rest of the letters. So I'm seeing sigma minus A2, and I continue this way. So basically, here we proved that the language LW is regular language. How we proved it? By construction. Just because we managed to build the automaton, that means that the language is a regular language. Any questions? Okay. If you don't have any questions, the next example. This example we had during the lecture. So basically, we need to build the automaton for intersection. So we have two languages and L1, words of odd length, and we have language L2 with automaton B, words ending with 0. So L2 is actually automaton A, L1 is actually automaton B. Now we need to define the automaton, which is intersection of L1 with L2. So basically, I would like to remind you that during the lecture, we started to build a new automaton, which was built from the couple of states. We took one state from automaton A and the second state from automaton B, and we construct the intersection automaton. The basic question I would like to ask is this automaton will be different from what we used for union. During the lecture, I constructed the automaton for union of L1 and L2. So the idea, should I use different states?
No, that's just the accepting states will be different.
Exactly. So basically, when I'm talking about intersection and not union, in union, I accepted the word if it belonged to language L1 or to language L2 or to both of them. Currently, when we are talking about intersection, the word is accepted if it accepted by L1 and L2. So if we are talking about and, like you mentioned, only accepting state would be different. So basically, I will construct the same automaton as I did for the union language. So we have a couple of state P0, Q0, P0, Q1, P1, Q0, P1, Q1. But now the only difference that we have only one accepting state, P1, Q1, because now currently if I want to accept the word, I need the word to be accepted by both automata, by automaton A and by automaton B. So basically I need to finish reading or accepting the word at state P1, Q1. So currently we know that only P1, Q1 will be our accepting state. In union automaton, I would like to remind you that we had P0, Q1 as an accepting state and P1, Q0 as an accepting state. So here we need only one state as an accepting state. Any questions? Okay. If you don't have any questions, now is the first question I would like you to solve. And I will divide you to smaller groups. So we have a sigma alphabet of 0, 1, and 1. And you have to build non-deterministic finite automaton that recognizes the following language. So the first language is the language of all words W, such that W contains even number of zeros or exactly 2 ones. And here you have a hint. You're allowed to use 6 states in your construction. So I would like you to ask to join breakout rooms. Basically, you just have to accept the invitation. You will see other members of the group, and I would like some of you to share the screen and to try to solve the question. Any ideas? Let's start building together the automaton. So we have even number of zeros. So I start with Q0. Is Q0 an accepting state? Should we accept an empty word? Can you hear me?
No.
No, because you need 2 ones.
Or exactly 2 1. 0 is
So
even.
we know that
So yeah,
Q0 is not an accepting state. Why not an accepting state? If I need or even number of zeros or exactly 2 ones.
Wait, but 0 0 is even.
Even if I have 0 0 zeros, then I know that it should be accepted.
If you have no zeros.
Empty word belongs to our language. Okay, but now let's see what I'm doing next. Next, I'm moving with epsilon transition to state Q1, where for each 0, I move to state Q2. And for the next 0, even number of zeros, I return back. And Q1 is an accepting state. Do you agree that Q1, Q2 accepts even number of zeros? Do you agree that the partial automaton Q1, Q2 accepts the even number of zero? I don't want to define what I'm doing for ones. Why? Because I'm using non-deterministic finite state machine, so I don't need to tell anyone what should I do for input 1. Okay, next transition. I'm moving with epsilon to the state Q3, and now I am accepting to receive exactly 2 ones. And if I'm getting these 2 ones, then I'm moving to state Q5, which should be an accepting state. And here, I would like only to concentrate on the second part of the language, where I was asked to do what? What was my second choice? Or even number of zeros, or?
Exactly
2 ones.
Exactly 2 ones. Do I have exactly 2 ones?
Yes.
If I continue to get ones at Q5, what should I do? I stay here. So if I have more than 2 ones, I'm moving. I'm staying at Q5. Away. Okay.
If you stay at Q5, then you have more than 2 ones.
And this is a wrong choice because I was asked to get exactly 2 ones. Can I get zeros after 2 ones?
Yeah, if they're even.
Okay. So basically, wait, why I don't have annotation? Wait.
This is not full, right? It's not a full solution.
No, it's not. It's a partial solution yet. I wanted to talk with you. So we know that 1 was the wrong choice. I need exactly 2 ones. So if I'm getting 3 ones or 4 ones, it's a bad solution. So what happens if I get a prefix of zeros before I get 2 ones? Should it be accepted?
It's even.
So if I have a prefix of zeros and then 2 ones, I should still accept the word. The input 0, 1, 0, 1.
Rina, why did you split it to 2 epsilons? What's the intuition to do something like that?
Because it was or.
Yeah.
So here I'm using the first part of or, even number of zeros. And here I'm building exactly 2 ones.
Oh, and then you combine them.
And then I combine it with epsilon transition because it's the easiest way. We will talk later if Q0 should be an accepting state, or if it wasn't an accepting state, it would be any problem. We will discuss it in a moment. So basically, in Q4 and 0, what should I do? Guys, state Q4 and 0.
How do you make sure it's an even number of zeros in the Q3 and Q5?
Yeah, you had zeros here. You had zeros.
I don't. It's once again, non-deterministic machine is a magic machine. If the word should be accepted because it is an even length of even number of zeros, I would jump from Q0 to Q1 with epsilon transition, and then I will count even number of zeros.
Yeah, makes sense.
Oh, okay. Should it be only even number of zeros?
Even well,
Without
in
anyone?
the bottom. In the bottom?
No, it's the upper part here.
Okay. Yeah. What about it?
Should it
Rina,
be
you
only?
really cut off.
Okay. Can you hear me now?
Yeah, you just on and off.
Okay. Okay. So basically, should I accept once in Q1 and Q2?
No.
When I was asked about even number of zeros, or exactly 2 ones, when I was mentioned even number of zeros, should it be only zeros, or it can be the word like 4 zeros and 1? Should it be accepted?
Yes. Yes.
Yes. So if we will go to the first part of what I built, it was not a correct machine, or it was still not complete machine. So I finished the major part, the even number of zeros, but I didn't draw anything that is related with input 1. So in Q1, on input 1, I should build a loop. In Q2, on input 1, I should be a loop.
Right.
So now an interesting question once again, how do I know to which state to go? So
you have 2 options, so it doesn't matter. If one of
I
them
have 2
will
options.
work.
If one of the options works, from my point of view, I solved the problem. So basically, you don't have a deterministic state machine with only one have automaton with states Q1 and Q2, accepts even number of zeros, but maybe there is also ones, but I'm not interested in ones. So it's a self loop in Q1 and Q2. If I decided to go with exactly 2 ones, then I move to the state Q3. And then for each 0, I don't want to know if I have even or odd number of zeros, but I'm interested only in 2 ones. So if I have 0, I stay in Q3. If I have 0 in Q4, I have a self loop. If I have 0 in Q5, once again, it's a self loop. But
it's
here,
0, right?
It's 0, yes. Okay. This one is 0. I don't have annotation. I don't know where it went, so I can't clear the screen. So hopefully I will clear it later. So do you understand the solution? Any questions?
What happens if in Q5 you get a 1?
If you have only 1, 1?
Now in Q5, what happens if you get a 1?
You don't have a transition, so the word won't be accepted. So for example, if I have 3 ones, after 2 ones, I'm at Q5 state. Q5 and 1 is not defined. It's an empty set. Empty set, it's a not defined transition. So the word will be rejected because I didn't finish to read the word and I had no transition, no place to go.
Q0 doesn't have to be accepting though, right?
Yes, exactly. So the next question that I mentioned that I will ask you later, as I've built an automaton. If, for example, I decide that Q0 is not an accepting state, is epsilon is still accepted?
Yeah, epsilon is nothing. You can always go that way. Yeah.
So if I cancel Q0 as an accepting state, let's see that I still have epsilon transition from Q0 to Q1, and Q1 is an accepting state. So epsilon is accepted even if Q0 is a non-accepting state. Okay?
I have another question.
Okay.
In the lecture, you did like this automaton, which is like a combination of both of both of them, like this one over like 2 slides ago.
Mhm.
And in this one, you just like actually took each one separately and just like they both have an like the empty word leading to both of them like separately. So when do we do this and when do we combine them into one?
When you have several possibilities to build something and something else and something else and something else. So if I have to build an and, which will be our next case, I sometimes have to construct states together. But if I have solution, something or something else, so basically the good idea is start at Q0 state and then to choose where to jump, or to the automaton which accepts the first part of the language, or to jump to the automaton which accepts the second part of the language. So Q0 and this epsilon transition means that we don't know from which state to start, Q1 or Q3. So we give 2 possibilities.
Thank you.
Okay. Okay. So we continue to our next question. It's the same question. I would like you still once again to try to use breakout rooms. And it's exactly the same question, but now I need the word W to contain even number of zeros and exactly 2 ones. And once again, you have to use 6 states. So you have, let's say, 4 minutes. I'm asking you to join the groups.
Okay, so Rina, we managed to do it. You're muted. You're muted, Rina.
Do you want to show it?
Yeah, I hope it's on the
So
screen.
in a moment, we still have someone missing.
Okay.
Yes, now everyone is here. So do you want to share your results with us?
Yeah, sure. You see it?
Exactly. So do you want, so let's only add an entrance arrow to Q0
Oh yeah.
to know that it's an initial state. Good, wonderful. So the idea is now that we have exactly two zeros, exactly even number of zeros and only two ones. So Q0, if we have even number of zero, we have a loop to Q5 and we go back. And if in Q0 we have one, we move to the new state. We saw one of only two ones that were allowed. Do you want to continue the explanation in Q1? What did you do?
Yeah. Okay. So we have an even number of zeros in here. So if you have one more one, you have two ones and even zeros, and it's okay. If in any case you deviate from the normal plan, let's say you have an odd zeros, you go here, and even ones, but still odd zeros, and you always can come back, and it goes all the ways.
Okay, so we have only two ones are allowed. The pass Q0, Q1, Q2, or the pass Q5, Q3, Q4 in this drawing. And basically, each time we have additional zero, we move all from the line of unaccepting states Q5, Q3, Q4 to the upper level where we have even number of zeros, or from upper level to the down level, which means that we have odd number of zeros. So wonderful, excellent solution, exactly what we were asked. Any questions from students who didn't manage to have this solution? No? Good. So if we manage this question, can I ask you the question? I don't want to do polls. Do you want to continue to use breakout rooms?
No,
Because
thank you.
I think it's a good idea for you to practice. It's not a problem. I can't solve all the questions, but I prefer that you at least try to solve them.
It's hard to communicate with you that way. Like we finished like a few minutes ago and we were stuck. And if we had a question, it would be the same. We can't communicate this way. So I think maybe.
Okay. So let's do the next question. Let's try to do it together. So the next question, can you see the screen as a question?
Yes.
Yeah.
Yes.
Okay.
What does it mean though?
So we have, we want to accept the language 0 in power of n, where n is a natural number. And I mentioned in lecture slides that natural numbers start with 1. 0 is not a natural number. So in the Hebrew group, we've had a discussion about it. And they told that in some courses, 0 is defined as a natural numbers. And in some courses, 0 is not a natural number. Okay, I use the definition of natural numbers. The definition of natural numbers that we have a set that starts with 1 and we increase each number by 1. So actually we will have 0, 0 in power of 2, 0 in power of 3, 0 in power of 4, and so on. So the first question, can I solve this question with only one state?
No.
No, why?
Because then you start with no zeros and it would be correct.
Okay.
With nothing, I mean.
Then If I have only one state, this state have to be an accepting state. This state has to be an accepting state. So Q0 will be an accepting state. And if Q0 is an accepting state, then I will also accept epsilon. And epsilon does not belong to this language. So to solve this question, I needed an automaton with two states. Let's see it. So basically, N, according to the definitions that we use, N is a set that starts with 1. So I need to build an automaton with two states. I'm interested only in zeros. I'm not interested in ones. And we have one in our alphabet, but I just don't use it. Q0 is not an accepting state because we don't want to accept an empty word. With 0, we move from Q0 to Q1, which is an accepting state. And if we continue to get more zeros, we still stay in state Q1. Any questions?
Pretty clear.
If everything is clear, let's go to the next question. Okay. Now we have additional problems. We will start with the first one. You have to describe. Describe means to build, and then to describe with 5 tuple the following NFA. The NFA, which accepts the language L, which has a prefix of zeros, 0 in power of I, where I modulo 3 equals 1, and suffix of 1 in power of j, where j modulo 2 equals 1. So I would like you to take at least 3 minutes and try to solve this question by yourself. If you want breakout rooms, I can allow you to work in groups. But I would like, first of all, each one of you to try to solve this question.
What's the minimal number of states? 4?
It depends how you solve it. I solved it with 1, 2, 3, 4, 5. I think I solved it with 5.
Okay.
I will give you additional time because only 25% of you finished the question.
Can I share the screen so you check if it's okay?
Okay.
I don't know.
But then the rest of the students will see it.
Don't pick, guys. Nah, I don't care. Your call.
Oh, just have patience.
I want to know.
Patience is a life virtue, Gal.
Okay.
Okay, let's sharing screen. Who wants to share? Nobody?
Gal does.
One sec. I'll do it. Not sure about it, but yeah.
Okay, exactly. So we have Q0 an accepting state. And with 0, we move to the state Q1 that indicates that currently number of zeros modulo 3 equals to 1. So now I just need each 3 zeros to return to the same state. So Q1 with 0, I move to Q2. And then I move from Q2 turn Q0 to Q0. And the additional third 0, I get back to Q1. So each 3 zeros, I continue to stay in this loop. Now, if I have odd number of ones, I will accept the word. So in Q1, if we have 1, we move to the state Q3, which is an accepting state. And we stay here for each time we have odd number of ones. So to continue to have odd number of ones, we need to have a loop with 2 ones. So Q0, Q4 gives us the loop of 2 ones. So basically, we are talking about non-finite automaton. Why it's not non-finite? Because, for example, for Q0 and 1, we don't have a definition where do we go. For Q2 and 1, once again, we don't have a definition. So now when we have a drawing, the next state or the next question is to define where do we move with 0 to give a 5 tuple. So let's start the solution of formal definition. So the set Q is someone else, not Gal, someone else wants to define the set Q. So basically you mention all the states. No, please keep your drawing. Okay, or I will share my screen because I think everyone is using.
No, it's already there, just the states and the lambda direct.
Okay, so let's see. The set of states, we have Q0, Q1, Q2, Q3, Q4. So we have 5 states. The alphabet is the same alphabet, 0, 1. The transition function delta. Q0, 0 is Q1. Q0, 1 is an empty set. Q1, Q2 is 0. Q1 on 0 is Q2. Q1 on 1 is Q3. Q2 on 0, we return to Q0. And for 1, the transition is not defined, so it's an empty state. Q3 on 0, we don't have a transition, so it's an empty state. Q3 on 1, we move to Q4. And the last state, Q4 on 0, the transition is not defined. Q4 on 1, we return to Q3. Okay, the starting state is Q0, and the set F of finite states or accepting states. F is only the state Q3, because only in state Q3 we have the number of zeros that divided by 3 gives us 1, and we have the number of ones, and we have an odd number of ones. So this is a formal definition, and that's what we were asked to do. Any questions? Somebody? Anybody? No questions? If no questions, we are moving to the next question. The next question, you have to describe, you have to give a formal description of this NFA. So basically, NFA is given. We just have to define a 5-tuple. So let's start to solve this question.
Do we need to add a column for the epsilon?
Yes. Since you have epsilon in your drawing, so when you draw the transition function, you should also mention not only 0, 1, but also epsilon. So let's do it together. The Q is, how many states do I have?
Q1, Q2, Q3.
Q1, Q2, Q3. So the Q is Q1, Q2, Q3. The alphabet?
0 and 1. And
0
epsilon.
and 1. Epsilon is not an alphabet, so the alphabet is 0, 1, and we use epsilon in our construction. Delta function, we will draw the table in a moment. The initial state is Q1, and the F set is accepting states Q2, Q3. Okay, so let's try to define our transition function. We have 3 states, Q1, Q2, Q3, and we have 3 columns. We have a columns for 0, column for 1, and column for epsilon, since we had epsilon transition. So the question can be asked, why in previous automaton we didn't add epsilon? Because the automaton was without epsilon transition. So if you add epsilon in previous automaton, you will just have an empty set as a result, so it's meaningless. In this automaton, since we have epsilon transition, it is a good idea to add epsilon as an input because it is a transition. So Q1 on 0, do I know where to go? Q1, 0.
It's a set. Q1 on 0, it's empty set, yeah.
It's an empty set. Q1 and 1, now I want to use 1, 1. So Q1, 1, I can stay in Q1 or I can move to Q2. So please pay attention. The resulting set is a set with Q1 and Q2. Please, I would like you to go back. The automaton we built for previous question was wonderful, but in transition function, and I'm sure that the exercise graders, checkers will pay attention. Please pay attention that you have to write a curly brackets near each state that you have. Because in non-deterministic finite automaton, the result of transition function is a set. Even when I have only one state, I have to write a curly bracket. So please add it to the solution we had before. And now I return back to our current solution. So Q1 on 1, I can stay in Q1 or move to Q2. So I define set Q1, Q2. Q1 on epsilon, I have an empty set since there is no definition. Let's see Q2. Q2 on 0, I can move to Q3, the set Q3. Q2 on 1 is not defined, so it's an empty state. Q2 on epsilon, I can move to Q3, the state Q3. But I write it as a set. Okay, Q3, we have only one arrow with epsilon that moves us to state Q2. So Q3 on 0 is an empty set. Q3 on 1 is not defined, an empty set. Q3 on epsilon moves us to a set with Q2 in it. Any questions? Okay. Additional question. Can you define what is the language of this NFA? Try to think one moment. You were not asked this question, but I would like you to give me an answer. What is the language of the automaton that we have here?
At least 1, 1. Starting with at least 1, 1. That's it.
Okay, that's it. And what about 0 from Q2 to Q3?
It doesn't matter. You don't have to have it.
Okay.
The suffix of zeros, but you don't have to have it. So
You don't have to have it, but if you only mention what you mentioned,
oh, on a partial, yeah.
if you have only prefix of ones, then you can have suffix with zeros and 1 combined, and it is not a correct definition. So the correct definition, you have a prefix with at least 1. This is a transition from Q1 to Q2, at least 1. And then you have a 0 or epsilon, and you have a loop of 0 of epsilons. So you have a suffix of zeros. I didn't mention how many zeros. So I can have a suffix of 0 zeros. I can have a suffix of 1 0. I can have a suffix of 2 zeros, 3 zeros, 4 zeros, and so on. Any questions?
Yeah. Why do you need to move from Q2 to Q3 with epsilon? Why not just stay in Q2?
It was given. The automaton was given. You can stay in Q2, but you can't miss Q3. Since Q3 is also an accepting state, you have to define what it adds to your language. And the addition, when I move to from Q2 to Q3, it can be the addition of 0, because epsilon doesn't add anything to my language. But the transition with 0 actually is very interesting from my point of view, because it adds something new to the language.
Okay.
So that is why I'm interested in Q3, and then the loop Q3, Q2, Q3 once again. Okay.
Thanks.
Additional questions? No? So please here, let's see. We are given a automaton. It looks alike to what we did before, but it's a little bit different. And the question is, what is the language of this NFA? So please take 1 minute, 2 minutes, and then we will solve it together. אוקיי, אני אתן עוד זמן, כי רק שני סטודנטים פתרו את השאלה בינתיים. אוקיי, בואו ננסה ביחד. מעבר, אוקיי, let's try together. The transition from Q1 to Q2. What is the meaning of this transition?
Least the prefix of 1, 1.
Okay, we have at least 1, 1 in a prefix. That is the meaning. Okay, please pay attention that now Q2 is not accepting state. We need to move from Q2 to Q3. And in Q3 now we don't have any loop. So when we move from Q2 to Q3, how can we move from Q2 to Q3?
0.
Or with 1, 0 or with epsilon. So when we define the language, we should define it. It is a language that have all the words with prefix of at least 1 ones and the suffix of maximum 1 0. Does this definition sounds okay? Any questions? Okay, if you don't have any questions, we are moving for our last question for today. We are giving an alphabet of 3 letters, 1, 2, and 3. And we will have to define the language that accepts all words that are divided into 3 parts. The prefix of 1, 1 in power of star. The middle part of 2's, 2 in power of star. And the suffix of 3, 3 in power of star. So basically, 1 can be missed, 2 can be missed, and 3 can be missed because the star operation includes also 0 concatenation of 1 with itself, or 0 concatenation of 2 with itself, or 0 concatenation of 3 with itself. So I can have words with 1s, 2s, and 3s, only with 1s and 3s, with 2 and 3, and so on.
Except
So,
in an empty state?
An empty state is also accepted. An empty word is also belongs to this language because I can take 0 1s, 0 2s, and 0 3s. So you have, let's say, 3 minutes each one to build deterministic finite state automaton that recognizes L. So please take your time and start drawing this automaton, and then we will talk about our possible solution.
Rina, how much is the NFA without and NFA with? How many states?
Without
The transitions of epsilon and with the transitions?
it will be 3 states.
I did that. Okay, without
NFA.
I did. Without?
Also 3, but I will draw it in a different way.
Okay. Thanks.
Okay, I would like to ask the question only about deterministic finite state. Did you finish the drawing of deterministic finite state automaton? We have only 4 answers, 5 answers, good. That's it, nobody wants to answer anymore. Okay. I will give additional minute to solve the question, and then we will solve it together. Okay, let's see my solution. Basically, I would like to have a loop of ones. I would like to move from the loop of ones to the loop of twos. And then I would like to move to the loop of threes and stay there until the end. So basically, Q0 is an accepting state since the empty word belongs to the language. So here, since we are talking about deterministic finite state automaton, I don't have any choices. Q0 has to be an accepting state. Until I have ones, I stay in Q0. So here we have 1 in power of star or 1 star. When I get 2, I'm thinking that I started to accept the loop of twos, and I move to the state Q1, and here I stay with each twos. So now I have 1 in power of star and 2 in power of star. If I get in Q1 3, I decide that I started to receive the suffix of 3s, and I stay in Q2 until I accept 3s. So to move to Q2, I have 1 in power of star, 2 in power of star, and 3 in power of star. Now I have to complete the solution. I was asked to build deterministic finite state automaton, and I have an alphabet of 1, 2, and 3. So since I have sigma that equals to 1, 2, and 3, I now have to complete my automaton. So in Q0 for 1, I stay in Q0. For 2, I move to Q1. For 3, I have to add a transition. So if after getting ones, I'm getting as input 3, I move from Q0 to state Q2. So we will be missing 2s, but we are moving to the state Q2. Now let's continue with Q1. In Q1, we know what to do for 2. We know where to go when we get an input 3. But when we get in Q1 an input 1, after having 2, I can't have additional 1s. If I'm getting any 1, I go to the trap state Q3, and I stay in this trap state forever. For any input, I stay in this state Q3. So I have only one state to complete, Q2. Q2, if on 3 I know what to do, I stay in Q2. On 1 and 2, I didn't define what to do. After getting the prefix of 1, the middle part of 2, and the suffix of 3, I can't accept any 1 or 2. So on input 1 or 2, once again, we move to the trap state Q3. Any questions about this DFA? Okay. The next question, the same question, but you are asked to use non-deterministic finite state automaton without epsilon transitions. Take 2 moments. Please think, what can you do with your deterministic finite state automaton to transfer it to non-deterministic finite state automaton without epsilon transition? Okay, only half of the students solves the question. I will give you additional minute. Okay, I would like to ask you a question. How do I transfer deterministic finite automaton to non-deterministic finite automaton that solves the same question?
Remove the trap state and
Exactly.
live in there.
Exactly. I don't need the trap state. The idea of what to accept is actually the states Q0, Q1, and Q3, Q2. Here I have the definition, the loop of ones, afterwards the loop of twos, and the loop of threes. What I don't need is the state Q3. So basically the solution how to build NFA without epsilon transition is just to delete the trap state. That's it. Okay, we are once again with the same question. Now you have to build NFA with epsilon transitions. You are not allowed not to use epsilon transition. Now there is a request. You have to build an NFA with epsilon transitions. Please think, how do you do it?
Not all of them have to be epsilons, right? Some of them.
Not all, but some. At least one epsilon transition you have to have.
Okay.
Once again, take 1 minute, 2 minutes, and we will solve it together. Can I ask you the question? You are only 8 students. Does it sound okay? What happened with the rest?
I
Do
guess
you know?
It makes no sense at all.
Because I guess because of how the lectures work, that the lecture itself is on YouTube, maybe people don't feel obliged. I'm sure the percentages compared to the Israelis are the same. they are just almost they are above 100 and we are 30 on a normal day. You know?
No, yes, it's exactly the same percentage. They were, I had only Monday group. Tuesday group I still didn't have. I will have the meeting with them tomorrow. So in Hebrew group, instead of 100 students, I had 38 students.
A third.
I think it's also because we moved the time of the class and it's late this time.
Okay.
It's because,
I don't think it's
because Zoom.
representable.
It's because it's people, I guess, don't feel obliged to come here. They can see the recording. I know
Okay,
it's not the best, but yeah.
Okay. Okay, who solved the question?
Me?
Okay, somebody else?
Yeah.
Okay. So what should we do? Where should I put epsilon transition?
Actually put it, I think, on everything. It doesn't really matter.
Everything. So I did something like this. I have three states, Q0, Q1, Q2, all of them accepting. Q1 is a self loop with ones, but now I can move from Q0 to Q1 with epsilon without any ones. Q1 is a self loop with two, and I can move from Q1 to Q2 with epsilon transition. And in Q2, I have a self loop with three. I used two epsilon transitions. So I managed to build NFA that accepts the same language. Did I miss something, or is any word that doesn't belong is accepted?
Q0, you don't have to make it accepted.
Q0 can be, no, yes, Q0 can be a non-accepting state, but it also can be an
Also
accepting
Q2.
state.
Yeah.
Exactly, also Q2, since with epsilon, I can move to the accepting state. So basically, someone who has the same automaton with Q0 as non-accepting state, it's okay. Someone who has the same automaton with Q0 and Q1 as non-accepting states, it's also okay. So basically, we finished what we were supposed to do. Any questions?
Yeah, we might get a question where we're limited in the number of accepting states or the number of, I don't know,
No,
epsilon.
but later we will learn the model how to build the minimal state automaton, not yet. But later we will learn the algorithm how to build the best automaton with minimal number of states. So currently you are all given the number of states that you should use, or you can draw the automaton that you like, but try to use let's say, the smallest number of states that you can see in your solution. The minimal number of states.